Hey guys, so this is gonna be me, Axiomatic Uncertainty, coming back with yet another video. This is my first video in a very, very long time. However, this is just an update on a project on which I've been working. Sorry if you hear some background noise; it's just the dog, walking around and stuff. Um, so it's an update on a project on which I've been working, which it's a reinforcement learning model for Tic Tac Toe. So essentially, if you've seen, if you're not familiar with reinforcement and deep Q learning, if you've seen like Google's AlphaZero chess AI or like the AlphaGo Zero AI, they both learned through reinforcement learning. And by reinforcement learning, I mean, playing against oneself in order to better, understand the relationships between actions and the future states of the game, including a win, loss, or draw of a game, in this case at least. So just, getting into the code a little bit, I'm going to avoid going too far in depth. We have our imports. Our reward discount had to be high since tic-tac-toe games aren't very long. And then we have two models. I decided to do one model for X and one model for O, seeing as, if you're the X player, you're going to take in a lot of states for like each of the squares on the board as a state, but I used one-hot coding. So then we have 27 inputs, which you can see here. And so I didn't feel like adding a 28th, to the thing for, which team it's on would necessarily be helpful. And so I decided to just create a second network with the, exact same feature set. So that's the way this is running. Now, we have some one-hot encoding functions here. This just creates a one-hot encoded version of the game state given. So we pass in a state and it returns a one-hot encoded state. Sorry, that's the dog. So the next thing that we're going to do is just, get the outcome of the game when we pass a state. This is just a convenient way of getting the outcome. This part is not necessary. I just haven't deleted that yet. This part, however, is the function that's used to determine what the end state of the game is if the game is ended. If the game has not ended, we just return a 0. And I'll get into why that's important in a bit, and then we return that. And then, we have a section that loads the models. And also a game processing script, which essentially just goes through all of the recorded games and, calculates the, it essentially creates arrays full of these states and then, calculated Q value vectors. So the reward vector, as I called it, is just a it's a 1x9 matrix containing our containing all of our Q values. So we initialize it with all zeros, and then we change the one value that actually was the action taken, the total reward multiplied by, and then this function, which is essentially just a way of determining what, this is just our reward depreciation, it's our discount factor, but this is just to determine how many actions we've taken, so it's essentially just to determine how many actions were taken between this point and the end of the game. And then, same is true for the other side. We shuffle our lists, and then we create one-hot encoded versions, and then we just train the models. This happens relatively quickly, and it's pretty neat that it actually works that well. Obviously, some optimization could be done, but since tic-tac-toe is such a simple game, I did not find that to be the most important thing in the world. And then, this is just to invert this variable. Xtrain is just a way of alternating between models being trained. And then down here, this is for user input, so we're just going to determine the mode. If we're training, we're going to go through all this stuff above. And so, if we're training, we do all of this stuff. E-greedy and whatnot are established below. E-greedy is actually some reward depreciation right now. Originally, I trained on an E-greedy value of like 0.2, since I thought having a lower epsilon greedy would make the model train better. However, running it... Okay, sorry, the dog just knocked something over. Running it on a higher value actually helped, in that, the model was just more exploratory, and tended to not stick with its decision so much, such that it actually got a lot of experience with like more generalized positions, and learning to approach things with more of like an actual strategy, like blocking and whatnot. Those are things that previously it hadn't really learned. What I had noticed in the past was that when the model was extremely simple, and the training was running on a low epsilon greedy, sometimes even 0, what was being observed was that the model didn't actually learn anything like blocking. Essentially, it just played the same pattern of moves every time, and the Q values just kept increasing because there was no reason for it to switch. It was just stuck in this pattern of doing the same thing over and over because it had a high probability of winning those situations. So this has completely turned that on its head. So basically this just does, all the computations we need. If the neural network is playing, we're determining, so, this is just like a way of, this part here, is a way of determining if we're going to make a random move, or if we're going to make, an AI chosen move. If the neural network is choosing the move, it just makes a prediction with the given board state, one hot encoded, and then, chooses the highest legal move, and makes that move. And that's why we have this for loop here, just to determine what moves are actually legal. And then we fill that square in with a 1 indicating an X at that location. And then the opposite is true here, -1, indicating an O, same here. And then we append that to the current games array. We also append the empty board, and we append this to our games array once it's finished. So that's pretty simple. The playing script is just a way of playing against the AI. You can choose your side since there are 2. We don't actually, I'm just going to delete this code. That was just some test code because I realized that there was a bug in my, there was a line that was just a bit wrong in my, outcome getting method. So, like, basically the outcome getter was having the issue that a state where the, either player has won by creating a vertical, 3 in a row down the rightmost column was being declared as not a win for some reason. And that was because of that weird for loop system I had before that was a bit wonky and convoluted. So I ended up replacing it with if-else statements, or if-elif, I guess. And then, we have some more stuff here. So choosing a side, right? And then once you've chosen your side, that determines in this, thing here. So this is just our way of determining if the AI is playing. That determines in our thing here which model is being used for predictions, and then accordingly which, type of, character will be filled in. The user just makes a standard. That's just a standard script for Tic Tac Toe, essentially. I'd imagine you would know how to do that if you coded in Python before. And then, we just, this part is just about converting it to an R board, aka readable board. And, we just replace them. So we replace an empty square or 0 with a dash, a 1 with an X, and a -1 with an O, and that makes it, comprehensible for the user. And then, we print out the board. We print out, first row, second row, and third row, all on separate lines. And then this part is just determining if the game has been won, and also determining if the game has, like, filled up. So basically what it means with this full variable is that if the game is, if the board has been completely filled and it's no longer playable, we end the game. And that's why, the get outcome thing only needs to determine if it's a win or loss, or, an unfinished game, or any, basically a win-loss or anything else, because this determines if the game has been finished, if it isn't a win or loss. So that's the entire code, 348 lines. Some of it isn't even necessary. So I would say Tic Tac Toe, if you're trying to get into, basic reinforcement learning, this is definitely the way to go. The network is very good at estimating Q values, actually. I was surprised by that. Sorry, the dog's getting particularly noisy at the moment. So, basically what we're going to do now is we're just going to choose a mode. So, we're going to do playing. Let's play as the X player. So, I'm going to go with the top right corner. And the AI plays this move here. I think this is a winnable situation for me. However, we will have to find... Yeah, it's winnable because I play here, block, I play here, and then I have a 2A win. So I'll play 4. That's weird. That's a bit odd. Usually it would block something like that. Here. So just to try something, let me actually... Okay, first let me check. Okay, so that's right there. It should be working just fine. So let me just do a quick check of some things. First, and this is an interesting thing that you should know is like, this just like, this thing's been training for like 20 minutes, so obviously it's not, perfect, but it's been pretty good, so I'm surprised by that. What I want to see here is what the Q values are. So the way you would do that in here, I'm sorry, the dog is being really noisy right now, is I would just go in and print, pre, and then basically what that does is print my prediction variable, and it gives me a vector of all my Q value approximations. Now if it's in CD Atom Ideal, I think. We're using the Atom, we're using the Atom Optimizer because that allows us to have, hyperparameter tuning for each of the weights, rates of change, and I think that that's better than just standard stochastic gradient descent. Additionally, the results are agreeable. So enough of that. Let's just run this. So if we run it in playing mode and I play a 0, that's weird. Didn't print my prediction here, so I'm sorry about this. I may even just skip in a bit if this is taking too long. Oh, I see. Okay, so it didn't print my prediction here. Interesting. It said AI is thinking. Why would it not just print the prediction? Interesting. So basically what I'm saying here though is that's okay. What I do think is weird here, honestly though, is that it played the right move this time. So I think last time it just failed to load the model. But what we're gonna do here now is just play 8, for instance, right? So it plays the ideal move for this situation, regardless of the fact that it's not printing the Q vectors. This is what I wanted to show you. So now if I play 3, for instance, which would be the blocking move, it's going to play there and set up for an attack. So I'll play a 2 and then a 7. So the game is, again, just played out like that. So that's a bit weird, though. Oh, I think I know what's happening. So what I need to do is I need to change my save destination. So we're just going to go in here and now save this modified version. And if we run it, we should see all of our changes. So basically what happened there was I moved the file this morning. I had it on my desktop for the longest time, but I moved it to that folder. And the editor, Sublime Text, thought that it was still on the desktop, and so it was saving my changes to the desktop when I hit Control S, which is why the game did not change when I actually made those changes. So I'm going to hit 0. Now you can see the reward vector has been printed. The middle was the top reply. You can see all these values are quite negative, but basically that's a bit odd. Yeah, so the middle was the top value with a 0.02. And that's, yeah, so that's what I figured. So now we're going to play an 8, right? And you can see that now the values have become more disparate. And what I mean by that is, like, you can see here this value, which is the 6th in the array, would be right here. That value is significantly larger than any of the other values. Additionally, and this is a cool thing that you could note, it has changed quite dramatically from before, whereas some of these values simply have not. For instance, this value has actually gone only slightly up from its previous point. Now, I want to show you something, which is, for instance, so let me block, and when I block, it'll put an attack in this direction. It should block, right? So we're going to see what the Q value becomes. So I block, and suddenly it plays here. This Q value is slightly lower than before. But what I wanted to show you really is, like, okay, so there we go. I play that, right? Now, here, right now, in this frame, the current Q value for this location right here, you know, or for this one, right, is, sorry, what am I saying? Oh, yeah, the Q value for this square, right, beforehand is negative 0.05, so it doesn't like that move. And, you know, it prefers this move because obviously this is the only move that blocks. However, following that, and actually, here's something that needs to be noted. The Q values are not going to be dramatic right now. So, like, you can see all these Q values are low. That's what I thought. At first, I was like, huh, that's kind of strange, right? The Q value should be higher because clearly, like, you know, why wouldn't it be more confident about its moves? Then I realized it's predicting Q values and not moves. So it sees this situation as a draw, right? Because this game is going to end in a draw. So the Q values are going to be low until something arises where that's not the case. So as you can see here, it's negative 0.05. But then when I make this mistake and play here, and it sees that this wins it the game, it becomes 0.64. So just a massive change. So I just think that that's interesting. So we're going to place the O player this time. And you can see place the corner. Now, if I play, say, a 1, right, it plays there. Now, this is a winning situation for the X player. If I block here, it plays here, ideally. And we will see if it knows the strategy. Yes, it does. So, what you can see is that this value here is low, right? This value corresponding to this square. It's low here as well, but not as low. And then suddenly, it's the ideal value by far, because the X player sees that there is a chance at winning. Now, if I block one square, for instance, this 3, it goes for the diagonal win with a value of 0.53 for the Q value. So I would say that in terms of confidence interval, after like 20 minutes of training, this is phenomenal. I would like to note that while this network does theoretically seem as if it's large enough to, you know, memorize most of the positions in this game, it doesn't really seem that that's actually been the case. You know, I didn't give it long enough to train for that to happen. It only really trained on, I think, like, maybe, you know, 200 to 300,000 games. And while the network is large, I have seen similar results when testing with smaller network sizes. So I don't really know that that's the issue, if that is, you know, a question of yours. So I would say that this is, like, you know, a complete success. So I'll probably give an update talking about, you know, how you can do this, and, you know, create like a Jupyter notebook or something like that, showing, you know, some of the steps to this. But other than that, you know, that's it for this quick, you know, deep Q learning update. It wasn't necessarily quick. And yeah, bye.